Okay, this is a big, exciting topic. We're going to actually talk about calculus here, and we're going to discuss what a derivative is. Now, the main thing to remember about a derivative is that it's just a rate of change. And in algebra, you probably heard that the rate of change is the same thing as the slope of a line. And that's what a derivative is. It's just a special case of slope. Except instead of talking about a line, we're talking about the slope at a curve. So let's say we've got a function here, f of x, and I would like to know the slope of the tangent line to this curve at x. Okay, so that's a bit of a problem because to get the slope of a line, I need 2 points. And if I draw a secant line between these 2 points, I can do the change in y of these 2 points over the change in x of these 2 points and get the slope of that line. But if I'm going to try and get the slope of a tangent line, it's not going to work because as soon as I do change in x, I'm dividing by 0. Remember that the slope of a line is your change in y over your change in x. And if that's 0, well, we've got some problems. Okay, so what we're going to do is we're going to move out just a tiny bit. And we're going to move out to x plus delta x now. Okay? So I've got 2 points. Okay, one point is where I want my line to be tangent. So the y-coordinate of that is f of x. And then the other point is just a little bit ways out from that point, and its x-coordinate is x plus delta x. And on the blue curve, the y-coordinate is going to be f of x plus delta x. Okay? So that means that our slope is going to be our change in y. So that's f of x plus delta x minus f of x, that's change in y, over change in x. That's x plus delta x minus x. And the x's cancel, and we get f of x plus delta x minus f of x all over delta x. So when would this secant line become a tangent line? When delta x shrinks to 0. And so to do that, we're going to take the limit as delta x, that change in x, shrinks to 0 of our difference quotient, our slope expression. And guess what? That's the derivative. After you take the limit, you have yourself a derivative. You also have a slope of a tangent line, which is a rate of change with absolutely no change in x. And if x was, say, time, that's how fast you're changing instantaneously or over an elapsed time interval of 0 seconds. Okay, so here is the limit definition of the derivative. And you may be wondering, okay, that's great. I can't plug 0 in for delta x, though, until I get rid of that delta x in the denominator. And let's see what happens when we have an actual function and an actual x-coordinate. So our function is x cubed minus 2x. We want to get the slope of the tangent line at x equal 2. And once we get the slope, we can use the point in the slope to find the equation of the tangent line. So here we go. I like to split things up into manageable chunks. So I'm going to figure out what f of x plus delta x is first. That's going to be x plus delta x cubed minus 2 times x plus delta x. Okay, now do you remember your Pascal's triangle? These numbers 1, 3, 3, 1 are going to be the coefficients of this binomial expansion. So I've got, here, let me give myself some room. So I've got 1x cubed plus 3x squared delta x plus 3x delta x squared plus delta x cubed minus 2x minus 2 delta x. Okay, so that whole thing is f of x plus delta x. If I take away f of x, which is x cubed minus 2x, notice that I'm going to subtract my x cubes, so they will be gone. X cubed minus x cubed, and I've got a minus 2x minus a negative 2x, so that's gone. And every term that's left over, all of these terms that's left over, has a delta x in it. So f prime of x is going to equal 3x squared delta x plus 3x delta x squared plus delta x cubed minus 2 delta x all over delta x, and we're going to take the limit of this. So let's see, let me grab all that. We're going to take the limit of this, and let me erase this real quick so I can fit it in there. As delta x approaches 0. Alright, so on top, I can factor out a delta x. And that's key, because once I factor that out, I can cancel that 1 in the denominator. So I've got delta x parentheses 3x squared plus 3x. That doesn't look very good, does it? Plus 3x delta x plus delta x squared minus 2 all over delta x. Here's the payoff step. Delta x's cancel. Now it is safe to put in 0 for delta x, and I get 3x squared. That term goes to 0. That term goes to 0. Minus 2. That is called our derivative. What does that give us? That gives us the slope of this function at any value of x. Well, I'm particularly interested in the slope at x equal 1. So f prime of 1 is going to be 3 times 1 squared minus 2, which is 1. Okay, so the slope of our tangent line at x equal 1 is 1. I'm going to go back to the original function, x cubed minus 2x, and I'm going to plug in 1. So that's going to be 1 minus 2, which is negative 1. So putting that information into point slope form, y plus 1 equals our slope times x minus the x coordinate. and that works out to y equals 1x minus 2. That's the slope of the tangent line to this cubic equation at x equals 1. And if you want to see what that looks like, I've already loaded that into the calculator here. So those are our equations. And here's my window. It doesn't need to be very big because we're only interested in what's happening around x equals 1. And here's our graph. Check it out. If I hit trace 1, that puts the cursor right at 1, and it's on the curve, the polynomial. Hit the down arrow, hit 1, and it's also on the line. So the derivative is really powerful when it comes to rates of change, because instead of being limited to an average rate of change, we can now find out how fast something changes instantaneously. So welcome to the wonderful world of calculus. I hope you see that it's not that scary. It's really just slope, which is something you've been talking about with lines since Algebra 1.